You may have seen several news headlines recently about quantum computing, particularly those pertaining to Microsoft's claims of being the first to create topological qubits. But what actually is quantum computing? In this series, we will explore what quantum computing is, the mathematics behind it, and what it is and isn't capable of doing that classical computers cannot do. In classical computation, the most fundamental object is the bit, which is simply a 0 or 1. All the computations performed by classical computers can be reduced to performing logical operations on bits. In quantum computation, the most fundamental object is known as the quantum bit, or qubit, a quantum mechanical system with two distinct levels, 0 and 1. Unlike bits whose state is binary, in other words only either 0 or 1, a qubit can take any coherent superposition of 0 and 1, akin to existing in both states simultaneously. However, note that if we attempt to observe the value of a qubit by measuring it in the standard basis, the state of the qubit will collapse to either 0 or 1, destroying this coherence and irrevocably disturbing the superposition. Okay, so given that qubits can take superpositions of computational states, it would seem that they are inherently more powerful than bits. Therefore, it seems natural to conclude that quantum computing should be able to accomplish more than classical computing. However, how does this advantage actually manifest? Well, we can consider this question from a few different angles. Firstly, let's talk about why quantum computation is inherently different from classical computing. One unique feature of quantum systems is known as entanglement. We will formally explain this term later on in the series, but for now, just know that entanglement basically means that the states of two qubits are correlated with each other. This non-local correlation cannot always be replicated with classical variables, a result formalized as Bell's theorem, which we will discuss in more detail later on. The second factor is the complexity overhead of simulating quantum computation on classical computers. In particular, if we have n qubits, we have that there are 2 to the n computational states, and since we can have a coherent superposition across all these states, we need to store amplitudes for all of these. For instance, if we have 100 qubits, to store a general state on a classical computer, we would need enough bits to store 2 to the 100 or approximately 10 to the 30 complex numbers, a feat which is obviously infeasible with our current technology. Moreover, since the quantum gates used to perform computation efficiently involve matrix multiplication, this makes computation intractable, as the complexity of matrix multiplication in this case is polynomial in 2 to the n. Okay, so now that we've discussed the advantages of quantum computing, how do we actually leverage these to do things that we can't do with classical computers? Well, one example of a property that we can leverage is known as quantum parallelism. In the classical setting, if we want to try compute a function on every n-bit string, we would need an exponential number of gates to do so, and if the function is not parallelizable, we may even require exponential time complexity. However, in the quantum setting, we can take a superposition across all n-bit strings and use the linearity of quantum gates to act on every single input with a single function call, meaning that we can effectively perform computation on an exponential number of values in polynomial time and poly-size circuits. This principle is used in many famous quantum algorithms shown to have exponential speedup over their classical counterparts. A prototypical example is Shor's algorithm for factoring large integers in polynomial time, a feat thought to be impossible for classical computers. Shor's algorithm is notorious for being one of the main factors sparking interest in the feasibility of quantum computing, as the hardness of factoring is a critical assumption for the security of the RSA encryption scheme, meaning that if factoring of large primes can be done efficiently, it would cause a cryptographic catastrophe, putting the security systems of the entire financial sector and governments alike in jeopardy. Anyways, we will discuss Shor's algorithm much later in the series once we have established the necessary background. Okay, so we've established that quantum computers definitely can do things that classical computers cannot, but surely there has to be some kind of catch, right? After all, it's not like quantum computers should just readily be able to solve every single problem that classical computers struggle with. Let's start by talking about the mechanical limitations of QC. To begin with, it seems as though quantum parallelism is all-powerful, as it means that we can compute over an exponential number of values in polynomial time, which should in theory allow us to efficiently solve a huge number of problems thought to be intractable on a classical computer. However, things are not so clear-cut. As an illustrative example, suppose that we have a function f that maps n-bit strings to either 0 or 1, where f of x equals 1 if x equals y and f of x equals 0 otherwise, for some n-bit string y. Suppose our goal is to figure out what y is. Classically, this problem would take exponential complexity, as we would have to check at most 2 to the n minus 1 values of x to find y. Now let's see what happens in the quantum setting. Creating a uniform superposition over all n-bit strings, we now compute f on each as follows. Note that y is contained in the superposition, and since we computed f of x for each bit string, we have that this particular computational basis state has a 1 appended to it, while all the others have a 0. Hence, if we can select the basis state with a value of 1 in this qubit, we could efficiently determine what y is. However, the only way to do this is to measure this qubit. Since the superposition is uniform, we have that with probability 2 to the minus n, the state will collapse to y1. Otherwise, we will get a superposition of all the states with x not equal to y. You might think that we can still find y in this case by simply figuring out which state is not included in the superposition. However, this cannot be done efficiently. Altogether, this means that we only recovered the correct answer with negligible probability, meaning that we will still need to run this whole algorithm an exponential number of times to reliably solve the problem. Therefore, while quantum parallelism does allow us to perform operations across a lot of inputs at once, we can only read a limited number of these inputs via measurement. Hence, to actually use quantum parallelism to improve runtime, we need to use some clever tricks to eliminate the states we do not want, which we will discuss later on. Furthermore, quantum computing has several practical challenges. Currently, there are 4 main experimental approaches to implementing quantum computing: superconducting qubits, atomic qubits, including both the trapped ion and neutral atom approaches, topological qubits, and photonic quantum computation. Each of these methods has their benefits and drawbacks. However, there are a few issues that are relatively consistent across most of these methods. For one, the error rate for quantum circuits tends to be significantly higher than that for classical computers, meaning that quantum error correction is an absolute necessity when trying to implement quantum algorithms for practical purposes with lots of qubits. However, this requires using more qubits and potentially introduces additional overhead, which can result in issues like decoherence. Hence, experimentally, quantum computation is something like balancing on a tightrope, and has therefore been challenging to implement thus far at larger scales. However, the field is rapidly growing, so who knows what might happen in the near future. That being said, regarding the recent findings by Microsoft, until further tests are performed to verify that a topological qubit was actually created, I would remain fairly skeptical about whether the claims they made are actually true. Altogether, quantum computing indeed has the potential to provide significant speedup over classical algorithms for several important applications. Nevertheless, it is important to acknowledge its limitations, both theoretically and experimentally, to not let ourselves get carried away. However, I hope that the otherwise bountiful potential demonstrated by quantum computation encourages you to join me along this journey of exploring the mathematical foundations of quantum computation and algorithms alike. I hope you enjoyed this video, and I will see you next time.